I'm going to skip the big picture of this class for a second, just because I want to make sure we have time to get through the rest of this cosmology stuff, and we'll wrap it all up. By the way, Thursday, last class, we will sew up any of your loose ends about anything we've talked about in this class. So, roll it around in the back of your head. If there's pieces of this whole story that don't make sense, let's air them out on Thursday. It's also my last time teaching at this university on Thursday, so I'm very excited to go out with a bang. So hopefully you all will be here, and we will have a good, rousing time. Yeah.
Did say you want to go out with a big bang?
With a big bang. There it is. So we cracked open the Big Bang. So guys, let's review. How did this happen? How did we end up, in the last century, how did we end up with this picture of the universe that was born out of this tiny little, infinitely dense point? How did this happen? Remind me what we talked about. Somebody. What is the Big Bang? Let's start there. What is this? I kind of just told you the answer, but yeah, go ahead, Kevin.
The Big Bang is a theory. This guy in Europe, I can't remember his country's origin.
Belgian, Lemaitre.
Yeah, Belgium. He had theorized, made this theory, and the church pretty much ran with it and spread it around, and blowing it out of proportion to where I'm pretty sure I can't remember where exactly. I think it may have been a video. Said he was like ridiculed by some people.
Well, yeah. So I mean, the Pope did run with it. This is a small part of the story, but I think maybe more importantly, what was it that the scientific community needed an explanation for? Yeah, go ahead.
So he had the theory that the universe was expanding.
Mm-hmm.
So going backwards from that, obviously, then that must mean everything came from a single point.
And why did he think that the universe was expanding, or what was the evidence that they were trying to explain? Does anybody remember? Well, what did this all come down from? There was a series of measurements done by this guy named Hubble, that we talked about. What did?
Light, right?
Yep. Well, what did Hubble notice? Back row, you guys awake? You guys, anybody remember what did Hubble notice? Yeah, Kevin. Or Evan, let's get Evan in, yeah.
Well, it was the red light shift, right?
Yes. So the bodies that he observed, and these, so he was working with Cephids, these pulsating stars. They were, the ones that were further away were redder, right? And there was a pretty, at least appeared to be a pretty direct relationship between the two. Distance was very tightly correlated to how red all of the colors were shifted. Everything was sort of less energetic for some reason that was far away. It's one way of thinking about it. All right, so this priest and mathematician named Lemaitre was the first to propose a mechanism, right? And it wasn't actually a super popular idea at first. So he proposed it, I think, in the 20s. I can't remember the exact year. Lemaitre, what's that?
It may have been early 30s.
I think it was like 28 or something. You'd have to...
29.
So Lemaitre writes this paper. People are like, it's kind of an interesting idea. Of course, the idea that the world hatches out of a single point is a really old idea, right? We actually see this in a number of traditions, pre-scientific traditions. It's a very common idea. And I think we discussed a bit last time about how this very much reflects our own lived experience on Earth, right? Everything we know of has a beginning and an end, including us, which is probably the most difficult part of reality to wrestle with. And in some sense, it's beautiful too, because it makes our lives extremely high stakes, let's say. You only get one shot at this, and it will, you guys are young enough that it seems distant perhaps, but it can be a very short ride unexpectedly sometimes too. So it makes sense that we might project that onto the universe, and that people, before science was even a notion, would have wanted to project that onto their understanding of reality as well. So it's a really old idea, I guess, is what I'm trying to say. This thing that Lemaitre saw in the data, in the redshifts, wasn't a particularly unique idea, which is what Kevin was getting at with the Pope being super excited because he thought, oh man, this is great. The mathematicians have proved that there was a creation moment. Of course, Lemaitre saw himself as a very serious scientist, and he said, dude, lay off it. This is my scientific idea. I don't want religious getting tied up in this, right? Okay, so then what happened? So I said people weren't, by and large, let's say scientists weren't by and large persuaded of Lemaitre's expanding universe idea. What was the alternative? Well, yeah, what was the alternative interpretation of that red light? Yeah.
Either that the light was just slowing down, losing energy over time.
Yeah, not necessarily slowing down, but the oscillations were slowing down. That's maybe one way to think about it, yeah. So,
Just
losing energy, right? So the energy of light waves, remember, light all travels at this, we can roughly postulate that light seems to travel its longitudinal propagation, the way that it moves across the room is at the same speed no matter what. But the individual transverse oscillations, right, the way the charge is oscillating at a given point, that reflects how energetic it is, right? So blue light oscillates really fast, red light oscillates really slow, and you can think of all of light on some continuum of blue to red. So the energy was just losing light was the alternative explanation. And nobody knew how that, sorry?
The energy.
The energy. The light was losing energy. Man, yeah. All right, talking, it's difficult. So that remains really honestly, I think that, and so people were proposing various mechanisms by which this would happen. Of course, they tried on all of the things we know that can redden light in our normal everyday lives, and none of them seem to stand up to scrutiny because they tend to blur out different colors versus others, right? And this, like I said, this redshift, this cosmic redshift, this distance redshift relationship, it holds the same for all wavelengths, which is really strange. People didn't have a process by which light would get tired operating on the time scales and the distance scales that we have access to in the laboratory, which kind of makes sense, right? And because I mean, how do you replicate in a laboratory a travel path that's millions of light years long? I mean, it would take you millions of years to do that experiment, even if you could set it up with mirrors and try to measure whether the light actually got tired or not. Even if you had a perfect reflective chamber, you'd still have to sit there for 25 million years to even see the effect, right? So that's probably not going to happen. So it's been a very, very challenging theory. It's called tired light in general. That's the name of this branch of explanations other than expansion for the redshift. And it's been a really difficult challenge for proponents of that theory because the experimental access isn't there and the known processes aren't there, probably for the same reason the experiment is difficult to pull off. It's just not something we would experience here on Earth, right? It's a cosmic phenomenon. So what else? So we get up to, so I think to some extent, life would have carried on as normal with these two sides, sort of both speculating in the background as to the cause of this phenomenon. But then something happened, which we're going to get into today. Yeah.
You brought up how for the tired light theorists it was hard because it was something that only happened out there in the cosmos and they couldn't be reproduced in experiments on Earth. And my thought was just well, that didn't stop the other astrophysicists for their other theories.
Exactly. Yeah. I think that's why I would speculate that if what we're going to talk about today hadn't been observed, I think that physicists would still be fairly split between this expansion idea and this tired light idea. I think that we would have pretty much two different camps that were constantly writing papers to justify their particular interpretation if all we had was the redshift. So the foundation of the Big Bang was originally just about redshifts. However, this happened, which is the subject for today. And this was the moment, I think, when the big bangers really won the contest. And it was a very interesting moment, and I really want to go through it in detail because to this day, the discovery of the microwave background is generally heralded as one of the most precise measurements ever made in science. It's one of the most thoroughly vetted. It's absolutely replicable. You can actually, there's YouTube videos where you could build your own antenna and measure the CMB from your backyard. So the interesting element of this comes down to what exactly is this microwave background thingy? Because the Big Bang, of course, the camp behind the Big Bang are absolutely convinced that this is a signature of the early moments of the universe. Whereas those who say have a different idea about what this red light means, about the origins or lack of origins of our universe they would have to interpret this signal differently. So that's what we're going to do, just like what we always do every class. We're going to look at two different stories about what this microwave background could mean. But first, we kind of have to understand what it is. So I think that we barely mentioned at the end of class last time this microwave background and the story about what it is said to mean according to the standard Big Bang cosmologists. Does anybody remember that? It was like right at the end of class. Anybody?
I remember that, but I don't know if I'm thinking of a conversation after.
That's fine. Fill us in. What is it? What is this? What is this signal that was detected supposed to mean?
The microwave background is a like I want to say universal constant. Is that correct?
It is a well. First of all, it's a radio signal that's measured. Let's just look at the story a little bit. So what was happening was Bell Labs out on the East Coast in New Jersey were building these huge radio horn antennas. They're basically these giant radio dish type things. You can see it actually behind these guys. This is the two engineers who were working at Bell Labs. And they discovered that there was this hum, this residual hum in their antenna. They weren't trying to discover anything. They were trying to build communication satellites. They discovered there was this noise, right? Now, I'm kind of getting ahead of myself because the interesting thing about this noise was that it wasn't just at one frequency. It was at multiple frequencies. So it triggered their minds and the minds of the scientific community about a series of predictions that had been made prior to this. So prior to this discovery of this radio signal, both the Big Bangers and the, let's call them steady state theorists, or like the eternal universe people, right? Because there's really only two options, right? Either the universe had a beginning or it didn't. It's always been here. Those are really, I don't know, does anybody have a third option? Maybe it had multiple beginnings and ends, I don't know. But something along that continuum, right? It either started or it didn't. So people, like I said, prior to the discovery of this, were pretty well split. The scientists were pretty well split between those two options. And prior to Lemaitre and the redshift stuff, pretty much all the scientists assumed the universe was eternal and had always been here. It was really only the religious camp that was arguing for a creation moment. So this was a radical change in the way scientists thought about things already. Even that half of them were even entertaining the idea that the universe wasn't eternal was pretty radical at the time. But even the eternal universe people imagined that there should be some background temperature of the universe. So all of the stars radiating all this heat and energy out into their surroundings would equalize with all of the dust and junk that's out there that we've talked about, and that there would be some sort of equilibrium temperature that was, you know, everything's cooling, everything's heating, but there's sort of this balance that emerges over time, right? So everybody was making predictions about what this temperature would be and if it could be discovered. So they were really on the lookout for it already. That's really important to remember. Now, it's kind of interesting because a lot of people made predictions. Actually, George Gamow was one of the staunchest proponents of the Big Bang Theory, and his prediction was actually an order of magnitude off about what this eventual temperature would be. And of course, they came up with these predicted temperatures based on their models of the expansion, right? So the expansionists, the Big Bangers, instead of imagining it being this equilibrium temperature of things, sort of heating and cooling at some neutral rates, right, which could be measured, they said that the background temperature would be a signature of this explosion that happened originally, right? And they made predictions on that. And the eternal universe guys made predictions based on their equilibrium ideas, right? And there was all these things published. So the story that the Big Bang guys were arguing was that what happens, and this is the one that's been sort of carried forward to the present, is that what happened is that there were no atoms or anything in the beginning. Actually, it was just light, right? It's very biblical. So there's just light in the beginning. Never mind what light is or how it happens or anything like that, or the fact that we've never seen light without atoms, but there's light. And all of a sudden, all this hot, dense stuff starts combining into atoms, whatever it is, this particle soup. And the atoms strain out some of the light that's bouncing around, and they let some of it through, which should sound a lot like the standard model of the sun, right? It's photons bouncing around for 1 million years before they pop out at just the right frequencies to give us that black body spectrum we see at the surface. So that's the story for prior to even the discovery of where this background temperature would arrive from, this background radiation would arrive from. And then what do you know? These guys are studying, they're building these radio antennas, and they discover, sure enough, there appears to be a light source that it doesn't really seem to matter where they point their antenna. So you can see this thing, it's kind of got a rotational axis, right? It can go side to side across the sky. They're actually trying to beam signals to other stations, of course, right? So it's sort of tilted. And they notice it doesn't really matter where they point this thing. They seem to always record this residual hum at multiple frequencies, and that if you stitch together those multiple frequencies, it basically seems to approximate that same nice black body curve that we get from the surface of the sun, right? We've drawn this thing a bunch of times in class, intensity, let's say, versus, wavelength. Should actually be, wavelength, right? It has this nice curve to it, right? They basically were able to fit the same thing onto the signal that they were seeing in the radio frequencies, right? Now, radio frequency, high energy or low energy?
Low.
Really low, yeah. Low energy, which means that the temperature that you get from the peak of this signal they were measuring was really cold, actually. It was only around 3 Kelvin, which is just above absolute zero. So really, really, really low energy, right? Really, really cold. So, immediately, and I do mean immediately, in the same issue of the same journal, in the subsequent article after this discovery was published, another group of mathematicians, let's say expansionist cosmologists, published an explanation of how this was the signature of the Big Bang. This was the residual temperature, the afterglow of the Big Bang, which is really remarkable. You almost never see something like that. I think I was talking to you guys after class last time. I mean, usually when you discover something weird in nature, you usually publish it, community argues about it for the next 5 or 10 years, and maybe somebody has a good theory. Sort of like what happened with Lemaitre. So Hubble published that redshift business. It sat around on the table for 5-10 years, and people argued about what it could mean. Lemaitre published his ideas. The steady state people published their tired light ideas. There was quite a discussion. That was not the case with this discovery by these two gentlemen. It was actually immediately heralded as proof of the Big Bang itself, which is perhaps an interesting lesson embedded in there if it turns out that they're mistaken about that. So this is, by the way, where their facility was. It's out on the east coast of New Jersey, right on the edge of the Atlantic Ocean. I'll come back to that in a second. So just to give you guys, this is kind of interesting. So lots of different predictions of what this thing would be. The closest was made, it looks like, around 1948 by a couple of expansionists who guessed around 5 Kelvin. Like I said, Gamma kept switching. By 61, Gamma was predicting 50 Kelvin would be the background. The guys who actually ended up sharing the Nobel Prize for this and published the explanation, they had predicted 10 Kelvin. This was actually a 3 Kelvin measurement, so that's kind of interesting all by itself. But what's most interesting is that the more they studied this thing, the more incredibly perfect of a signal it looked like, actually. So over here is a picture of the sun. If you look at the spectrum of the sun outside of the atmosphere gobbles up a lot of its frequencies. But if you just look at the sun, you see that it has the surface of the sun, the photosphere has an almost perfect black body. Not quite. There are some problems with it, but it's basically a rainbow of colors centered on the visible range, right? This is the microwave background at a temperature of 3 Kelvin. This is at 5,800 Kelvin, right? The sun's much, much hotter, obviously. But if you look at this data, it's incredible. So this data that was actually captured, so they started, after the first article was published, they started sending up weather balloons to see if it was, where it was coming from. And the weather balloons recorded an even more intensely precise signal. And this one was actually taken by a satellite that was right at the edge of the Earth's atmosphere in low Earth orbit, called Kobe-Fearus. We'll look at that data a little bit more in a second. But what's really remarkable is how incredibly precise this black body spectrum is. There's absolutely no question that this is a Planckian spectrum of the highest caliber that we struggle to even get recordings of in laboratories of this kind of precision. If we take a graphite black body chamber in a laboratory, we can maybe get something that looks like this. But in nature, we've never seen anything like this before, which is really, really astounding. So, on one hand, we have this genuine experimental evidence of this incredible black body spectrum whose source appears to be diffuse. We don't know where it's coming from exactly, right? On the other hand, it's immediately converted into evidence of this beginning of the universe explosion. Now, given everything we've talked about in this class, what's the problem with attributing a signal like this to this, gaseous plasma at the beginning of the universe? Back row? Front row? Yeah. Go ahead, Kevin.
There's, we haven't fact-checked it. We haven't accounted for any variables with the atmosphere, because you said this was ground-based.
Well, what's the problem with pointing at a black body signal and saying it's a gas? I guess is what I'm trying to draw here.
Gases can't produce black body spectrums; they only produce single colors or wavelengths of light.
Yeah.
And the whole idea of the Big Bang is not even just that it's from just gas, but even just light. Just because somehow light exists without gas, and that creates perfect spectrum.
Yeah, it's a deeply material. Well, first of all, it's missing a material basis for light, but I mean, that's a huge problem for everybody. But yeah, more importantly, we never ever see black bodies from gases ever, anywhere. And the only way that these people were able to argue that it came from this gas at the beginning of the universe is because they point to the sun and they point to the stars and they say, well, the stars can do it and they're made out of gas. which is really, really strange if you think about it, because it's the ultimate circular argument in some sense, because you say, well, are they though? Are they actually gas? And if they're not, then you have nothing left in the entire universe to point to that can give you this beautiful continuous spectrum from a gas. Yeah, go ahead.
But they also can't be liquid because the Big Bang doesn't give enough time for that.
Well, yeah.
It's an entirely
Yeah,
circular.
that's a huge, huge situation. Yeah, well, again, if this hadn't been discovered and immediately attributed to the Big Bang, I think people would still be fairly well split over the two possibilities. The steady, they call it steady state. It doesn't mean things don't change. It just means there's an equilibrium between the formation of new galaxies and the death of old ones, and it's a very steady, cyclic metamorphosis, right? But I think that the scientists would still be split between the two. In fact, one of the biggest proponents of the eternal universe was this guy named Fred Hoyle, who was a real titan of a scientist as well. But after the CMB, he kind of walked away from the table a little bit, which is, perhaps a very quiet tragedy that deserves a Hollywood movie at some points after this all sorts itself out. So, yeah. So this is what we have. We have a microwave signal that it's called a microwave signal because it's a really cold black body, right? Really, really cold. Or at least gives us a temperature that points to something that's very cold. Or low energy, because cold and low energy are the same thing, right? So of course the Big Bang was supposed to be really, really hot. Why is the temperature of the thing so cold by the time that we see it, according to the Big Bang theory? It's probably more bizarre than you think, but yeah, go ahead.
Because it's lost all its energy, because it's so old, so lost all its energy.
You would think so, yeah. That'd be a pretty good explanation. That is unfortunately not the explanation, though. Explanation is that the universe is expanding, so all the waves have expanded, so it's red. It's moved into the low energy spectrum. Remember, in the standard approach to physics, light is sort of this magical thing. It doesn't have a material basis, so the idea that it's even being relayed across neutral atoms has not made its way into the textbooks, although I've kind of been working off that assumption this entire course.
Light is material, space is material, then how does space expand and that affect light's wavelength?
Well, it isn't for these guys, so they don't have to worry about that, I guess.
So space isn't what? Oh, great.
Yeah. Yeah, it's a real doozy. That's why this is such a fun topic, because it really concerns the way that we make sense of reality at the most core level, right?
Or don't.
Okay, so we have this beautiful black body spectrum. We measure it pretty precisely at that radio horn on the coast of New Jersey. Send up weather balloons. The error bars get even smaller. We send a satellite up above the Earth, albeit right above the Earth, and it's some of the tightest error bars we've ever gotten on a black body ever, right? Pretty crazy. So, what do we want to say about that? All right. So then later, maybe you guys, I think one of these images probably makes it in your textbook, if not these three themselves.
I've seen that lower image.
You've probably seen this low one a lot. The cosmologists love this picture. Now, why do they love that picture? Well, they love that picture because it's an image that was, it's not really an image, first of all. It's a map of radiation intensity that was measured very far away from the Earth at a point called L2. We've talked about L2, but it's a little stable gravitational point on the far side of the Earth-Moon system, right? So they took a satellite, plopped it out there, and they collected data for a long time. And they come back and they've made this map, and they say, look, we have measured the fluctuations in this microwave signal, right, at really high resolution. And so this is the one that often makes the headlines and stuff when people talk about the microwave background. Now, what they don't tell you, though, is kind of interesting. So The actual microwave signal was never measured at L2 with the WMAP satellites and the Planck satellites. What they did, actually, in the case of the WMAP, is they assumed the temperature and the frequencies of the microwave background, and then they took a horn that had they took an antenna that had two horns pointed in opposite directions, and they rotated them around. And so they calibrated what they expected the signal to be off of those measurements they made back at Earth, and then they went looking for the difference in that expected signal in all directions. Now you could do that with literally anything, anywhere. I could go into this room, assume that there's a signal of whatever I want in any direction, and I could make a map of the difference in that signal. I could do it with blue light or any light in this room. I could make a very similar map, actually. Now, it's shocking to me because I've spent hundreds of hours with cosmologists, and very few of them even realized that this was the design of the WMAP satellite. And the Planck satellite was very, very similar. Instead, they actually had a reference load that was like a source of light that was calibrated to the microwave signal back on Earth, and they compared the differential measurements to that. So they didn't actually ever measure this thing anywhere away from Earth, which is something that's lost on even PhD astrophysicists. Most people don't realize this, which is really shocking that they didn't do that, because it would have been a very easy measurement to do. The only thing I can come up with is that they were so absolutely convinced that this was a cosmic signal that they didn't think it was even necessary to build into their satellite. So the question still remains,
Their theory would be null and void because it wouldn't be measured outside of Earth.
yeah, I don't even think they were just so much in love with their theories, they just assumed they were right. So, you know, there's a very open question about whether, I keep calling this thing the microwave background instead of the cosmic microwave background, because I'm not sure that it's cosmic at all, actually, which is what I'm going to try to point to here today. Because it hasn't been measured away from the Earth ever. And so that should really be an interesting red flag for us when we realize that only liquids and solids can make that kind of signal, that black body signal. When we realize that all of our observational evidence here on Earth only points to the ability of actual lattices to do that transformative process of turning heat into light, light into heat. It seems like materials need to be present to pull that off, right? The fact that we haven't measured this microwave background away from our own Earth should be some sort of a serious red flag. So, by the way, not to just be someone who's complaining all the time, but I mentioned to you guys at the beginning of the course that I've started working with a group on building a satellite to answer some interesting questions about the sun. One of the really easy experiments we're going to do on our way to imaging the sun is we're going to measure this signal as we move away from the Earth. Now, if the signal actually comes from the cosmos, which it might, either way it might, then we should actually get a better and better picture of it the further we get away from, you know, whatever sort of noise is around the Earth, right? However, if it's local to this planet itself, then that signal is going to disappear immediately. So that'll be a really easy question to answer that nobody's actually answered yet. Okay, so we really have two possibilities appearing with our story here today. One, this thing, there's actually three, but I'm going to break it into two first. One is that it comes from the cosmos. The other is that it comes from the Earth. If it comes from the cosmos, does it come from the beginning of time, from this gaseous plasma, or does it come from some sort of equilibrium radiation with all of the starlight interacting with all of the junk in space? So there's kind of three possibilities as far as I'm concerned for what this could mean. Yeah.
Oh, the real answer hasn't been found yet?
Well, it depends who you talk to. Yeah, so. Honestly, I actually have friends in all three camps, which is really interesting. So I have a good friend who's a physicist down in Brazil who's spent his life just translating historical texts. And he's gone through all of the old predictions throughout the 20th century. Because remember, all the eternal universe people were making predictions about what the temperature would be as well. And it turns out they were actually a lot closer to the one that was discovered. So my friend, Professor Assis, is convinced that it is probably an equilibrium temperature. It has nothing to do with the Big Bang. It's just an equilibrium temperature from basically all of the thermal absorbers, all of the chunks of ice and soot and stuff that are out there that are radiating in this kind of background flux. My friend Pierre, who I've introduced you guys to in terms of this liquid sun model, he kind of resurrected it himself about 20 years ago and wrote the 40 proofs paper that's in your Moodle. Pierre is staunchly convinced that it comes from the Earth. And of course, the Big Bangers are staunchly convinced that it comes from the beginning of time, right? So, you know, I think that there's a lot of other sketchy business going on with these maps too that I kind of wanted to point out. So when they actually measure, first of all, this is what the actual maps look like. Okay, this is the way that it's kind of distorted in these actual maps. You can see the signal's kind of lopsided. And remember, this is just a differential map that they made of the radiation at some particular temperature that they're looking for in the sky at L2. They say that, okay, well, it's skewed because the Earth is actually moving through the solar system. So there's some sort of Doppler shift that warps the temperature map a little bit. So they apply some algorithm to correct for that, right? And what they get is something that looks like this. Now, as you can see, there's huge bands of radiation in the plane of the ecliptic, with respect, or at least, sorry, not in the plane of the ecliptic, in the plane of the satellites. Now, what is that, first of all? Because that doesn't show up on these nice maps that we looked at earlier, right? This is gone. So what is this? Anybody know? What does it look like?
Is it a satellite itself?
It's the galaxy. So the galaxy is an incredibly powerful microwave emitter, as you might imagine. I mean, if all of the stars are giving off all of this light, the tail end of this is going to go off into the microwave. You add up all those stars, you're going to end up with huge microwave sources, plus not to mention all of our hyper-energetic events that we've talked about, star formation, novas, all of these things are expected to contribute in some sense, right? So what they actually measure is a huge, huge contribution of the galaxy. Again, they delete that mathematically. So they delete this, they delete that, and they end up with the map thingy that you see all over the PopSci tables or magazines. So the question is, can you actually, is it actually, we picked on the Big Bang picture a bunch in terms of data filtering, right? And data filtering is a really, what did I say?
You said Big Bang picture?
The black hole. I'm sorry, thank you. Yeah, really having a hard time talking lately. We picked on the black hole image in terms of data filtering, which was, by pretty much all accounts, a horrendous amount of data filtering. Data filtering is a really, really scary, sketchy business in science. It's not that you can't ever justify it, but you got to be really careful about that. You have to be sure that what you're filtering out is something that you can actually justify. The problem with filtering out the galaxy from these cosmic microwave maps is you don't really know what the contribution of the galaxy is because it hadn't actually been studied in this same way before, right?
That was going to be my question. I was like, how can you now, say that it isn't just that all of it is not just.
You can't. That's the problem. Yeah, that's the real problem.
Where do you draw the line? Because if I look here, do I say the stuff that's red is the galaxy, or orange, or yellow?
Well, the red's the heat. That's the most intense parts of it. So yeah, presumably the galaxy is the source that's dominating the signal. Actually, yeah.
There's also something to be said, why, if we're seeing this with our galaxy, is it really far-fetched to say that other galaxies also do this?
You're right.
I mean,
right.
We use our sun as a point of reference for other stars, so why don't we use our galaxy for the reference of others, even though it doesn't necessarily exactly match up all the others? So I brought this up in one of our after class conversations about something I was kind of thinking about in the back of my mind of like what if the microwave background is just like all the other galaxies, like light that just couldn't necessarily reach us in any other form.
That's a valid hypothesis. I don't have the answer, and I think that is one of the three real possibilities. I mean, one of them, again, it could be a background, it could literally be background light that has a physical basis in black body physics, right? That is a possibility. Could just come from all the other stuff, right? Could come from the beginning of time, or it could come from the Earth. Now, the reason that I'm a little bit partial to the Earth thing is the error bars that have been measured on this thing, right? So one thing that's kind of interesting is that when you go out to L2 and you make these differential maps, right? They aren't direct measurements of the CMB, but they are some sort of differential map where they look at the fluctuations in radiation in both directions, right? And the whole point of the maps is that there's pretty serious fluctuations everywhere, actually. But when we look at that picture of the data from low Earth orbit, those error bars are tight, right? There's almost no error on that signal, right? So it's really, really pristine, at least near the Earth, which is, very, very strange if it's a cosmic signal. Yeah.
I was gonna ask about that because you were talking about how precise, unnaturally precise it seemed that the black body spectrum was for it, but then the data if outside of on in at L2 is literally just differentials. All they're measuring is how imprecise it is.
It's very interesting, right? It's an interesting argument. Now, again, this could all be cleared up if they'd actually gone ahead and measured the monopole. That's the direct signal. If they'd gone ahead and actually measured that at L2, that would have really cleared things up, perhaps. But it was not, and it hasn't been done yet. So very, 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 very cheap, easy experiment to do. And I hope to see that one at least accomplished in the next few years, which will be really interesting because I think it will point us towards one of the two possible material explanations for what's going on here. Okay, so we got all this image processing background stuff. Again, I guess I kind of already blew the lead on this, but most people don't realize that the actual W maps, the W map, the Planck, these CMB pictures you see everywhere, they're not actual direct measurements of the CMB. They are differential radiometers that assume the CMB exists. They assume it's cosmic. They assume the temperature. They assume the power density. They assume everything from the Earth-based measurements, right? Particularly from that Kobe-Fearis horn, which was the satellite that was plopped right above the atmosphere. So now let's look at the Earth a little bit. So I want to talk about the Earth as a potential black body source itself, which is a little bit strange. It's a strange idea, and it requires us to sort of think about sources of black body radiation from all around us, actually. We get a few clues, actually, not from the science community necessarily, but actually from people who build satellite communications, the communication satellites used for our cell phones and stuff. Now, one thing that's really interesting, actually Pierre dug this up, is that in these journals, when you read about how they calibrate the position of their satellites, so these satellites, by the way, are all also very close to the Earth. They're a number of dozens of kilometers above the surface of the Earth. But they're all basically in low Earth orbit. And that's why they're so useful to us, because we can ping our cell phones off of them or whatever. One thing that's really interesting, though, is that these communication satellites, they calibrate their position based on a number of different things. But one of the things they use is the CMB. Now, when they are looking for the strongest source of the CMB, where do you think they point their satellites? Yeah,
at other satellites, or like at the
Well, if you want to measure something that's coming from the cosmos, where would you point your satellite?
ideally out.
Ideally, you'd probably point it out into space, but that's not what they do. They actually point at the edge of the Earth, which is really, really weird if you're looking for a signal that's supposed to come from up above you. But for some reason, these are completely disinterested parties. They're not scientists. These are people who run telecommunications companies. They're engineers and stuff, right? So when they go looking for the strongest source of this ubiquitous black body radiation, they actually point their satellites at the edge, what's called the limb, right? The curve of the Earth. And that's where they measure the most intense aspect of this radiation. That's pretty bizarre. Now, if we go back and think about the COBE satellite that was, yeah.
I think it's also important to mention that the engineers don't have any ball in the game.
That's it, yeah.
Theory or whatever. They're just doing what works.
Yeah, they're just trying to make their satellites work, right? And they're like, oh, we have another calibration source, and we can use it, and we find it most intensely over here, which is just like kind of an interesting, bizarre little feature, right? Because if this is a cosmic source, and again, this is perhaps argues in favor of it not being a cosmic source, which again is a super easy question to answer, and I think we can answer it in the next few years, but they don't seem to be pointing at the cosmos, which is really, really strange and bizarre. So now, what about this COBE satellite? So the one that made those beautiful error bars that I showed you guys at the beginning, that beautiful black body spectrum. That one was pointing at the sky. But there's a problem with that. The problem with it is that it had a horn that looked like a giant tuba, basically. And it didn't in any way consider that the source of that radiation might be underneath behind it. And so its engineers didn't concern themselves in any way, shape, or form with shielding radiation that might arrive from diffracting over the edge of the horn itself. And this may be what's happening, actually, with this experiment in particular. So, you know, these guys were very, very careful when they were building this Furus horn, this COBE radio satellite. They were very, very careful when they were testing it on Earth to avoid large bodies of water and things like this. Now, why is that? First of all, you guys ever used a microwave oven before?
Yes.
What do you do before you cook the ramen noodles?
Put water.
You put a bunch of water in it. Why?
Microwave cycle water.
Because the water is extremely sensitive to microwaves, actually. And as we know, anything that absorbs a given frequency can also emit that frequency. Go ahead.
If it wasn't for the fact that almost all of our food has water in it, you would not be able to cook it in a microwave oven. Without water, microwaves don't do much of anything.
Yeah, that's exactly right. So it's those microwave ovens all work on the basis of exciting the vibrations in the actual OH bonds, for the most part, of the water. Now, so water is actually, the more you look at water and the more you think about it with radio waves and microwaves, the more you realize how incredibly interlinked the two are. So this is a huge problem, obviously, for you know, when people first started doing submarines and stuff, right? No, this is like the plot points in Hunt for Red October or something. I don't know if you guys saw this movie before your time. But as soon as you dip down, like, you know, inches below the surface of a body of water, you can no longer transmit radio waves. They're completely absorbed, which also, of course, means that they're completely emitted as well from the substance, right? So, you know, this is by itself a really interesting clue about the situation. However, scientists are hip to this, right? So you guys have seen these maps maybe, especially during the global warming crisis when everybody was talking about the oceans warming and all of this, right? They can take satellites, these NOAA satellites from, you know, the climate scientists will actually point they'll point, let's say, radio telescopes at the oceans and measure the temperatures of the oceans, right? And what do they find? Well, they get more or less accurate temperatures of the oceans, Now, they don't do this quite by making a whole black body curve of it. They actually just sort of pick some frequencies from the projected place where it would fall, and then they back calculate the temperature of the peak from that. But it's a pretty reliable method. You see guys doing this at the grocery store and stuff too. I was just at Costco today, and there's people walking around with these IR thermometers, right? They're basically making approximations with one frequency of the whole black body curve because they assume that they're on the slope somewhere. They back calculate the peak temperature as a result of it. So when they actually point their antennas down at the oceans, at the water on Earth, they can actually measure a decent temperature as a result of that. And it's what? How hot is the oceans? Pretty warm. I mean, they're certainly well warmer than the 3 Kelvin of the microwave background, right? They are hundreds of Kelvin, right? So, 200, 300 Kelvin, probably 300 Kelvin-ish, right? Let's just go with that kind of room temperature oceans on average, I suppose, probably a bit colder. All right, so that's something we have to contend with because the direct measurements of the oceans gives us a very different temperature. So, this is probably perhaps why nobody even thought about looking at the oceans when they were trying to make sense of this microwave background, because the temperature is different that we measure with this microwave background. So we have to think about that. However, water is quite interesting stuff when it comes to optics, right? We were talking about this after class last.
It's 276
276.
something Kelvin on average.
So water, and actually all materials, if we all condensed matter, we've talked about this, that when you modify the lattice, how the atoms are bonded to each other, you get different optical properties, right? This is the diamond versus soot thing that I've been going over with you guys a lot. One thing for certain is that water is no exception, actually. So during these nuclear tests that were very popular back in the 50s and 60s, one of the things that people noticed was that when you set off these bombs on the ocean, there's a shock wave that expands from the point of detonation. And that what it does is it compresses the water where the explosion is happening. And what you see is a beautiful ring of black water that moves away from the sites of the explosion. Perfectly opaque black water. Now, why would this be? Water is generally fairly transparent to light, right? Of course, it disperses it to some degree. There's some refraction and stuff, but all of a sudden the water becomes black when it's compressed. What do you make of that? Yeah, what do you think?
It affects the water's relationship with light in some way.
Yeah, but how? Yeah.
It changes its structure.
Yeah, I mean, you've literally just completely rearranged the lattice. They're under incredible, gigapascal levels of pressure inside of that ring where the nuclear explosion is going off. And you've somehow modified the lattice of water. You've compressed the lattice of water. And now all of a sudden, instead of being transparent, the water is completely opaque. It's a visible light. It's black, like a black body. It's like a very, very black body in that compressed region, right? So this is interesting. And it should point to the fact that water has the potential to have multiple different optical regimes that it operates under. So most people don't know this, but water actually occurs in layered-like structures. This is particularly evident at surfaces. So this is a kind of microscopy. I actually did this kind of microscopy when I was doing my PhD. It's called atomic force microscopy. It's like a pretty bizarre, it's not technically the kind of microscope where you look through something and you see light coming back at you, that you magnify the light. With atomic force microscopy, what you have is this tiny little maybe a micron wide little cantilever. It's a bendy little thing. And what you do is you shine a laser off of the back of this thing. So any small changes in the cantilever's deflection get amplified onto some sort of photosensor. So you can actually see how much your little cantilever is getting bent. So the way that they reconstruct these images is they actually see how that cantilever gets bent as it punches through each layer of the water above the surface here. And that's what we're seeing in these images, is a layered-like structure of water in these experiments, right? Now, in terms of places where this might occur, you know, in terms of large-scale lattice, like layered-like organizations, one thing we know for sure is that our best black bodies that we can make in laboratories are made out of this stuff for the most part. At least they were in the early days. They've got some really fancy new lattices that they use as well. They still obey this same basic principle. That's what they're shaped like, right? What is this?
What?
This is ice, actually.
Same
So water, when it's cooled, it actually forms the exact same, not exact, it's actually bent a little bit. It's a puckered kind of hexagonal lattice. But it is a very beautiful hexagonal lattice that has a lot in common with our black bodies from the laboratory. So the question remains, can water in huge bodies under all kinds of interesting tensions and pressures, as a giant body would be, is it able to act as a black body? This is a really interesting question. Now, certainly if it does, it's not a perfect one, because if, as I'm pointing to, the oceans are actually the culprit here, well, the temperature that the black body of the oceans is giving us isn't the right temperature, obviously. We know the oceans aren't 3 Kelvin. We also know that we can measure the OH vibration of water quite easily, directly. And we know that that gives us not quite the right temperature, but close, very close. And the fact that it's not quite the right temperature is also quite interesting, too. So, what could be happening here? There's a couple of interesting things here. So, one thing that's kind of interesting is with this actual particular antenna that was used with Kobe. Yeah.
On the previous image,
Yeah.
red, the hydrogen, and the blue.
The reds are the oxygens.
Oh, red is oxygen, blue is hydrogen.
Blue is hydrogen, yeah. So this kind of lattice, by the way, yeah. So what kind of lattice is that? Like, what is the bonding that's inside of ice? Does anybody know this?
The blue inside the red.
What kind of bonds are formed inside of ice? Does anybody know? You may have heard this in high school or something. What are they called? It's a very particular kind of bond. It's not quite the same that's in like a metal or something like that. Because you can break ice up pretty easily, actually. It's called a hydrogen bond, right?
Oh, right, yeah.
So this lattice is actually a hydrogen bonded lattice inside of ice. This hexagonal lattice is actually a hydrogen bonded lattice. Now, what's really interesting is that many of the properties we attribute to water, you know, the fact that it forms that it's very cohesive, right? Droplets like to group together. That's due to the hydrogen bonding. In fact, all of the properties of water that kind of hold it together, all of its surface tension, everything is due to the hydrogen bonding, right? So that should also give us pause to consider what's going on here, because remember, the temperature that we're actually measuring with those nice IR cameras and stuff, the energy that's being pumped into your ramen noodles is going into the OH bonds. So the water, let me just make this absolutely clear for you. The water has a big old oxygen, and then it has 2 little hydrogens stuck onto it. That's the basic, and these guys are stuck together somehow. Let's not even worry about that. These are the H's, this is the oxygen. The thing that is being measured with those IR sensors is the energy tied in this bond. It's actually the wiggle of the hydrogens as they are bounded to the oxygen. But there's no accounting for the hydrogen bonds, actually. So they don't make it into the calculus, actually. which might be why that temperature that we read from the oceans isn't quite up to par, right? When we do these thermal imagings, like the NOAA studies and stuff, they're always a little bit short of what they should be. We also have this bizarre 3 Kelvin bin to take care of that we don't know what the heck that comes from. Although, of course, the Big Bangers have decided immediately that it is from the Big Bang. But if it is not, all of a sudden we have an interesting piece of the puzzle to perhaps account for this. So there's this really interesting phenomenon too, where, if you actually do these sensors and you actually look directly if you use an ordinary radio telescope to get the temperature of, say, any object really, what you'll find is that the angle at which you're actually pointing your telescope is going to radically alter the perceived intensity and therefore the temperature of the body that you're measuring. And so,
I think that's obvious.
what's that?
I feel like that's obvious.
It is. It's a well-known phenomenon, right?
So, like if you turn a camera, the image you're gonna get's different.
Yes. Yeah. So this is one thing that's quite interesting. So actually the different polarizations, so what they do whenever they do radio telescopes is they have polarizers. These are kind of like the sunglasses or whatever. And they basically screen out one polarization of light. Remember, light is this transverse oscillation. So if the atoms emitting it are all lined up together, it's all going to be oscillating in the same direction. If they're not lined up, if they're just kind of chaotically organized, like the surface of the sun or something, they're going to be oscillating in every direction. But you can filter out each polarization and record it separately. But in either case, as the angle goes off to the edge at which that light is coming into the antenna, the temperature of it goes down precipitously as well. This is just a measured effect. So this is regarding the actual kinds of satellites that, say, those guys with the communication satellites are using as well. They would experience the same effect with the temperature that they measure. So what could be going on? The proposal is something like this. There's 2 bonding networks actually in the oceans themselves. There's the one that you use to nuke your food in the microwave, the OH bonds, these guys. And then there's the bonds between the actual waters themselves, which are hydrogen bonds. These are the bonds that form the hexagonal lattice in ice as well. And that in these giant bodies, you're actually able to observe 2 different optical signals, right? And that the one that's actually, so I have these 2 sets of arrows drawn here. Remember, black body radiation never has polarization to it. It's always chaotic. It's being emitted in every direction. However, the OH bonds are preferentially aligned, and they do actually emit with different polarizations. And they spread out in such a way that they actually don't make it down to the zenith, right? So if we go and look at the edge of the Earth, if the water from the Earth is emitting light, the OH bonds are going to leave a little shadow at the lim, right, down near the edge, whereas if there was a black body source of the ocean, it would be emitting much weaker, but from the hydrogen bonding network, it will be emitting in all directions, right? So it'll be completely drowned out if you stare directly at it from above. But if you get down at the edge, down at this 90-degree angle, you actually might have a chance of observing it, which seems to be exactly what's happening with these communication satellites, who are only able to resolve this 3K background, microwave background at the limb of the Earth, right? Here's another angle. By the way, my wife made these pictures. Thank her very much. We were trying to visualize this last year. Okay, so
Very good job.
she did, yeah. So the question remains: is it possible that Penzias and Wilson, with their horn antenna plopped at the edge of the Atlantic Ocean, were actually measuring the hydrogen bonding network, the compressed lattice structure at the surface of the ocean? Is it possible that there is structured water at the surface of the ocean? Well, there's good reason to believe there is. I don't know if you guys have ever spent any time by the ocean where there's lots of ships coming and going. Have any of you lived by the ocean? Spent some time on vacation? It's kind of crazy if you actually watch. I was watching this last time I was down at the bay. You know, a big freight liner or something can go by and you can actually see the surface of the water being completely structured and different for an hour after the thing passes. You actually can see the mark of that boat for a really, really long time.
Wake.
Beyond the wake, even after the wake is maybe the wake's the turbulent part, right? But even after that, there persists a very interesting structure at the surface of the water for a very long time. Now, that doesn't surprise anybody because people generally assume that water is quite a structured entity and that it does maintain these long-range orders across time, right?
Like, how else does it have big waves?
Well, the waves are kind of a macro phenomenon, but I'm talking about like the actual water molecules themselves, right? There's something about the surface smoothness of the water which has changed and leads to different reflections and stuff, right? It's a very micrograined process that must be responsible for these phenomena I'm talking about with the trails of the boats that have gone by, right? So we still have our three possibilities. We have the possibility that this microwave background truly is cosmic. And of that possibility space, we have the possibility that it comes from this plasmatic gas at the beginning of time. We also have the possibility that it is cosmic and it comes from the other galaxies. It comes from equalization with all of the junk that's out in space, that it really is just a cosmic glow. And then we have the possibility that it comes from our own oceans, which is really all of these seem like they could quite easily be sorted out. Yeah.
Could it be both the water and like the background heat of just Nazi? Could it
Yeah.
combine?
I mean, all three of these are really theories. I think they're all like fairly, you know, I think that for me, you know, having gone through this entire course with you and looked at the different possibility spaces that emerge if we recognize that stars give us a beautiful black body spectrum, that black bodies require a lattice. In particular, it seems like some sort of, not just any lattice, but they really like these hexagonal lattices a lot. With that in mind, it makes it, you know, really hard for me to understand or really buy the story that it comes from this gaseous plasma at the beginning of time. As far as the other two possibilities, I truly don't know. I don't know. And I do think, like I said, I think we can answer it really easy. All we do is send a satellite to go take our beautiful pictures of the surface of the sun, and we just happen to measure the CMB along the way. And what happens? I don't know. You know, I don't know. Maybe we leave it behind here at Earth, and that solves the question. Maybe we don't, and we have a much bigger, and that also solves the question. Now we can scratch one possibility off of our lists, which would be really nice as well. So,
Or maybe it just gets weaker as you go away from Earth, but there's still something there.
yeah. I mean, that would be interesting too. Any of these things, whatever we learn, will be super interesting. I really think it's a super easy experiment. It can piggyback on pretty much any satellite that leaves the Earth. It's a really cheap instrument, these radiometers. I mean, we could just measure a few frequencies to approximate the black body spectrum. It's not a big deal. It's like 1970s technology. We just, you know, screw one of these things, bolt it onto the back of a satellite that we're using for something more technical. We can answer this really, really easily, honestly. So I expect, you know, that this would be a very different class 5 years from now if I was able to differentiate between those two possibilities. But I do think they're both tantalizing. I think the one that Kevin brought up, this being a genuine cosmic signal that reflects something about everything else that's out there, that's really interesting. That seems possible for sure. That it could be coming from the hydrogen bonded network of water seems absolutely possible as well. And I don't know, I don't know any better way to answer that than to simply kick a satellite away from the Earth and see what it sees, because that hasn't been done. And I think the take-home message that's really important here is that most astrophysicists and cosmologists have no idea that it hasn't been measured away from the Earth, right? They tend to rely on this picture that's been taken at L2. It's not really a picture, but this map that's been made, right? Without really stopping to analyze the instrumentation and realize how that map was made. And it's really shocking to me, the more of these people that I interact with, how none of them realize this. It's not so much a secret, but you would have to actually read the paper to understand how they made this map, right? And even the people who were working on it, it was such a foregone conclusion about the calibration of these sources that they didn't even realize that they were relying on something that had actually come from Earth in the first place. Yeah.
How can you be a scientist of a subject and not read the paper that's behind one of the fundamental theories of that field?
You don't have time, I guess? I don't know. I mean, this brings up a bigger question, and maybe we can discuss this at length during our last class, but there is a huge there's a lot of huge questions about the way science is done in general that have hopefully emerged in this class.
And you're studying for that. Shouldn't we be made to read the paper, the fundamental, one of the fundamental papers of the fundamental assumptions?
I think in the future we might, but I think it might take a mistake of this scale for people to realize that the way that we're educating our scientists is a little backwards, because I didn't have a single day when I was doing my PhD to read the foundational papers in my discipline. It was all about inheriting the knowledge set that was assumed and reading the contemporary papers that would basically tell me what needed to be done on the experiment that I was working on. And this is generally how science education works. The higher you get up into it, the less time you have to go back to the foundations, right? It's really, even people who go on at other universities to become astrophysicists or whatever, they're still sitting through these introductory courses like this, which is really the only time they're going to have to examine the foundations of the discipline that they're entering into. It's not a lot of, and this is a new way of going about things. So I think, if you go back to and look at the way that people were educating their children, at least the people who are, let's say, the nobility and the educated classes, because of course most of the world was agrarian peasants for almost all of time. But there's always been educational programs going back to the Greeks. If you go to ancient China, ancient India, there's always been an educated class. And the way that they educated people was generally going to the classics, right? Generally going to the foundations of knowledge and really re-examining and questioning them and really squaring off some of these foundational ideas and trying to conclude which ones of them make sense and which don't. We don't have a lot of time for that these days in our technical pipeline, right? When people are training, they're training to make for the most part, most of the people who go to do PhDs in astrophysics and stuff, where do you think they end up? Let me ask you this. All of my friends who were doing PhDs in those disciplines when I was at Columbia, where do you guys think they're all working at right now? How many of you think that they are still doing research and they're professors, let's say? How many of my friends are professors? 0. Where do most of them go to? Yeah.
I was thinking the military or NASA.
Yeah, they go to do engineering, right? They go to make those communication satellites, right? They're very practical. They go work for DARPA. They go work for Palantir, right? They go where the money is, or maybe they even just go. I have another friend, one of my closest friends, who is a big collaborator on my work. He went straight to the financial sector, worked for Wall Street. He's really good at math and numbers, and they love that stuff because you make predictive models and make money on it, right? So look, most people are not training in the sciences in order to continue to do science. They're training so that they can get the skills necessary to get a job in the engineering, financial sectors, stuff like that. There's almost no professorships left in the universe. Basically what happened was, boomers got those jobs back in the 70s, And they've sat on them ever since. And they're not making new professorships. They've actually been slashing them. So there's really no future for people who go into science other than going into engineering afterwards. That's a bit of an overstatement, but it is kind of true. So again, I think that perhaps the most interesting thing that's come out of this course, and I'll let you go because we can break this all down in its full elaboration on Thursday, is that there could be some beautiful stuff by way of a renaissance that comes out of making mistakes as big as this, right? Because if we really do have to face down the fact that we've misunderstood the stars, the galaxies, the whole universe itself, the cosmology, then maybe we have to sit down, look in the mirror as a society and say, we need to go about this a little bit differently. And that could be one of the most beautiful things that ever happens to science, actually. All right, let's talk about it on Thursday. Have a good week, guys.